My session is called Scaling Up, and as we've just been talking about, it's not just about throwing more people at problems. And so I think it's worth thinking a little bit about what is involved in building bigger, more complex software. I think that one of the things that we often do when we think about software and software development is kind of inform our thinking based on our real world experience. And there's a problem with that, is because software is not the same as these other forms of development, these other forms of engineering. There are certainly analogies that we can take, but this is not our problem. One of the rather unique things about software, one of the things that software in general delivers that is unusual in the world is this. It's that our product is a sequence of bytes, and that sequence of bytes is as close to free that it doesn't matter to reproduce. If we are building physical things like aeroplanes or cars or cups or pens, then reproducing those things on a mass scale is a difficult problem. And it's a problem that we never ever have. However complex our software system, ultimately it's just a stream of bytes, and we can clone that stream of bytes as many times as we like, essentially for free. So that's kind of weird. That's kind of a strange thing about software. It means that we don't have a production problem. Our problem is something else. And so when we talk about scaling up software development, we don't want to try and employ the approaches that are typically used to scale up things like car manufacturer or aeroplane manufacturer or iPhone manufacturer. That's not the same thing. So we need to think about that. So this is not our scaling problem. Scaling up production is not the problem, because that's cheap and easy. We can just copy the bytes. It's something else. So applying ideas like production line thinking is wrong. It's a mistake. It's not about trying to come up with cookie cutter solutions because or standardized approaches, because those are the tools of production lines. Those are what you do when your problem is about recreating the same thing over and over again. Our problem is really different, and I would say that it's fundamentally about two things. The first one is this: software development is an exercise in learning and discovery. However good we are, however experienced we are, when we come to a new software, a new task, a new project in software of some kind, then we don't know the answer, kind of by definition, because if we did know the answer, we'd use the answer that we had before because it's free, because we have the bytes, the bits and bytes that represent the answer. So we don't know the answer, so we're going to be discovering new answers all of the time. Now, they might not be new to the world. I'm not saying it's like new scientific research every time we do software development. It's not. But it's going to be new to us. We as individuals or as teams or as organizations are going to be learning. And so we should be good at learning and discovery. If we want to optimize for learning, then there are some behaviors that are necessary for us to do that. And the first on my list is iteration. We need to do work in a series of short steps. We want to make progress in small steps so that we're able to learn, so that we can make a change, observe what happens as a result of that change through feedback, collect the feedback that we gather from the change, and understand the change better and what it means and how it moves us closer or further from our goal. We also want to think about kind of incremental work, and by this I kind of mean modularizing the stuff that we're working, so that we can kind of work on one part of the system without affecting another part of the system, and that too allows us to focus in the sense of learning on what that one part needs to do in isolation, in a little bit more isolation. Now, the the gold standard, the world-class approach to learning, I would argue, is science. And science is based on experimental practices. We try out things, we carry out experiments, and we understand what we learn from those experiments. And so if we want to become world-class experts at learning within our discipline, then we need to work in ways that are experimental. It means that we need to risk failure, we need to take chances, we need to try things out that we don't yet understand in order to get deep in our understanding. But organizing our work and thinking of what we do as always experimental puts us in a much stronger position to benefit from the learning that we can gain and to regularize and organize that learning. And lastly, we want to be empirical. Software development operates, software systems operate in the world, and the world is a messy, complicated place, and we're not going to get them right all of the time. So we need to learn what happens to them in discovery, and we want to carry our experiments out into production and learn from production and the real world, as well as more theoretical evaluations within tests or within our development process. So these are the kind of tools and techniques about that will allow us to become good at learning. And that's one aspect that allows us to scale up our understanding over time. The other thing that's important about software development, and particularly doing it at any scale, is it's all about managing complexity. If you think about the ideas in programming languages and your designs, usually what you're trying to do is that you're trying to manage complexity in one part of the code so you can ignore it in another in some way, or you're trying to constrain the complexity. If you're a functional programmer, you try and constrain the complexity of software development by limiting your ability to assign things to and change the values of variables. If you're an OO programmer, you limit the complexity of things by encapsulating information and sending messages between pieces of the software. But it's all about managing complexity. And I think that, we should be thinking about that very clearly too. Too often I see code bases that seem like a kind of linear stream of a linear stream of consciousness, and just a series of steps with no real organizing principles. You see this in anti-patterns like large methods or large classes, where you thousands of lines of code that just kind of wander around doing all sorts of different things. That's not really organized at all. It's just kind of a sequence of instructions, a recipe rather than a code base. And so if we were going to work to be able to manage complexity, we need to start thinking about what that takes. And I think that there are another 5 things that kind of crop up in that space. We need our system to be modular so that we can work in one part of the system without impacting another. We want to use abstraction. We want to hide ideas and information and implementation details between different parts of the system. So again, we can make progress in one part of the system without caring about what's going on in another. We can use ideas like separation of concerns, trying to ensure that our systems do, each method, each class is focused on achieving one goal, and it does that well. We don't want, if you look at a function and you says this function does this and this, it's probably a mistake. It's better if it just does one thing. And we want to try and organize our thinking that way so that each part of the system is clear what the outcome of that part is about. We prefer systems with loose coupling, or at least appropriate levels of coupling, so that we can move pieces around and we can kind of reuse pieces of ideas that are good and useful. And cohesion, we want the bits of code that are closely related to be close together, in the ideas in code, I should say, that are closely related to be closely positioned in the code. One of my favorite descriptions of good design comes from Kent Beck, who said that good design is moving the stuff that's related closer together and the stuff that's unrelated further apart. It's kind of a joke, but it's kind of also deeply true. So modularity and cohesion are kind of foundational principles in ensuring that our code is good in some manner. Now, one of the things that's kind of interesting when we start thinking about scaling up and doing this for more complex systems in bigger organizations with bigger teams maybe, is that information is a kind of a slippery idea. There's something profoundly basic about information. There's even an attempt at the moment, something called constructor theory, about trying to rewrite physics as an information theory. But there's something profound going on here. And so one of the things that we can say is that the organizations that we work in and the teams that we do development in are information systems as much as the software that we build. And so some of the ideas that I'm talking about here are just as true of the organizations in which we carry out software development as they are of the software that we build. And this is certainly commonly captured in ideas like Conway's law, but it goes further than that. There's a lot of stuff, ideas that are common and common problems in organizational structures that are really, we would recognize as software people. So what do we need to do? I think some of the things that we should be thinking of in terms of understanding our discipline better, and so better applying ideas that work for us, is to first recognize that software development is a creative discipline, and work to ensure that we can work in a creative way. We are literally creating things in terms of the software development, but it's creative in the same way that other forms of engineering are creative. If you are Elon Musk building spaceships in South Texas, then that's a creative thing to do. You are being inventive and coming up with new ideas and figuring out how to solve problems. That's our bread and butter. That's the stuff that we software developers do all day, every day. Dependencies in code and organizations are caustic. They are one of the most difficult problems. When people talk about the difficulties of scaling software development in any context, it's nearly always down to how do you deal with the relationships between different parts of a system? How do you worry about doing work in one team that has an impact on another team? How do you worry about the interfaces between two pieces of code, and so on? And so I think that one of the ways that we can start to achieve this is recognizing these problems, these attributes of software development, and apply creative engineering thinking to software to solve these problems. The principles behind this, to my mind, are that we need to optimize for learning. We need to become experts, world-class, lightweight scientists in terms of our approach to learning. We want to also optimize to manage and limit the complexity of the systems that we build. Some of the tools that we can use to achieve that is that we can exert greater control on the variables in our space. Things like infrastructure as code, deployment pipelines, automated testing are ways in which we can kind of control the variables in order to measure the behaviors, the functioning, the performance of our software, for example. We want to make better evidence-based decisions. An awful lot of software decision making seems to me to be based on guesswork to a large extent. And so I'd rather move away from the guesswork and try and come up with rational explanations. And the best way to do that, to my mind, is to start to think of what we're doing, everything that we do, as some form of an experiment, and then figure out how we would capture the results of the experiment. How would we measure what's going on? And I don't mean this in a complex, overbearing way, but you could think of a simple unit test as a small, simple form of experiment. You can think of collecting data from production as a slightly more complicated form of experiment. You could think of changing the way that we organize our stand-ups or our requirements process or how we sit as forms of experiments. If you think about those in those terms, it just changes your mindset slightly about how you approach that. If it's an experiment, then you probably want to have a hypothesis. You probably want to predict the results. You're not just going to randomly try stuff, and you're going to be in a better place to make these evidence-based decisions. The other science idea that I think is profoundly important, and we were chatting about this at the start, my current video kind of talks about this, is always start out assuming that you don't have the correct answers. Assume that you're most likely wrong. And if you work that way, you're going to work in a slightly more defensive way so that you give yourself room to be wrong. And if you are wrong, it's easier for you then to recover and to get back into a better position, a stable position. So starting off with kind of what in science they would call a skeptical mind is a good thing. And lastly, in these things that we can learn from science is to, instead of try to prove that your ideas are correct, try to prove that they're not. We can never, however many automated tests we have, we can never prove that our software is good. But as soon as we have one failing test, we know that our software is not good enough, and therefore we can reject that change. That's a better way of working, a better way round of working in general. Falsification is a stronger principle and is kind of fundamentally part of the way that modern science is organized these days. Falsification is better than proof, because falsification is more definitive than proof. A simple example, I can assert that all swans are white. You can't prove it, I can't prove it, nobody can prove it. But as soon as we see one black swan, we know that all swans aren't white. We've falsified that idea. So it's a powerful tool that we can use in software. I think there are another couple of valuable tools, and these affect profoundly the way that I approach software development, and these are testability and deployability. Let's start with talking about these and think about the testability of our systems and what that means. So, as a starting point, what is it that we value in good software, in good code? And I'd argue that I'm going to give you 5 things, and you may think of other things, but I don't think that you will disagree with my 5 things. Sorry, there's 6 because I've added it has to work. First, it has to work. That's important. Now it's modular, loosely coupled, cohesive, good separation of concerns, and exhibits information hiding or abstraction. You probably recognize these ideas from what I was talking about earlier. So let's just look at each of those ideas briefly. I'm going to whiz through this quite quickly. Modular code is separated into independent modules. The idea is that internal details of individual modules should be hidden behind a public interface, blah, 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 blah. This allows us to decompose problem into smaller pieces. Solutions are more independent, solutions are more composable, so the system is more flexible. We can reconfigure it in different ways to get different kinds of behaviors. It often also means that our software is more scalable as a result, because we can make it more elastic. We can have many different versions of one piece or one version of another, and so on. Loose coupled. Loose coupling is an approach to interconnecting components in a system so that those components depend on each other to the least extent practicable. This reduces the risk of change in one place affecting another. It kind of reinforces the ideas of modularity so that one piece of the software can care less about what's going on in another one, and it allows each to move more independently of other pieces. It also helps us to decompose big problems into smaller pieces that more easily fit into our head when we think in these sorts of terms. Cohesion is the flip side of modularity, really. It refers to the degree to which elements of a module belong together. And cohesion matters because it focuses on reducing module complexity. It stops modules being too chatty with other modules, and so it helps us with reducing the coupling too. It tends to improve the maintainability. If all of the ideas that are related in one place, that makes code easier to change. And again, it helps us to gain more reuse. If we've nicely compartmentalized our code so that the related ideas are close together, we could use those related ideas in different circumstances, perhaps. Separation of concerns. Separation of concerns is one of those ideas that really I use as a very, very significant tool in my own design approach to design. It informs my decision making when designing quite a lot. Separation of concerns is a design principle for separating a computer program into distinct sections so that each section addresses a separate concern. So the colloquial way of capturing this is one class, one thing, one method, one thing. We want each piece of code to be focused on doing one thing and doing it well. It tends to simplify development. It simplifies focus. It makes things easier to test in isolation from other concerns. It tends to, again, reinforce the ideas of reducing coupling and improving modularity. And it tends to simplify maintenance overall. Testing improves significantly when you have a system that's got good separation of concerns. And the last of my list is information hiding. They are not, in computer science terms, information hiding and abstraction are not completely the same. I do tend to lump them together in this. Information hiding is a powerful programming technique because it reduces complexity. And one of the chief mechanisms for hiding information is encapsulation, blah, 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 blah. So this is about trying to draw lines in our system so that there's a difference. You know, on one side of the line, there are one collection, you know, there's a collection of ideas, and then that's hidden. Some of the detail of those ideas, how that works, what it means, is hidden from the other side of the line. That's really what we're talking about, drawing these seams, these joins in our software that allows us to understand better the system overall. It allows us to kind of surf over the complexity of the system at some level and not always be looking at every last detail of every last part of the system when we are thinking about it. It tends to reduce coupling, tends to improve cohesion, aids modularity and separation concerns, and so on. So what allows us to add those properties into code? Before test-driven development, remember we're talking about testability. This was only down to the skill, experience, integrity of an individual programmer. It was down to how good somebody was, how much they cared, how much effort they were putting into doing a good job. That was it. That was all that was involved. Test-driven development is an approach to software development, and my favorite way of describing it is red-green refactor. We're going to do that over and over again. We're going to write a test and we're going to run it and we're going to see it fail. Then we're going to write some code to make the test pass, and we're going to run it and we're going to see it pass. And then we're going to refactor the code and the test to make them beautiful and elegant and more generic while we're in a stable position and the test is passing. So unless you are some kind of crazy person, then you want to make your life easier. So at the point at which you are writing a test and you haven't got any code yet, you'd be kind of insane, or at least rather dim, to make your life harder. So what do? You make your life easier by making it easy to write the test. You make the code testable. You design the code to be testable, because you'd be daft to do anything else. So what is it that makes code testable? Well, testable code it works. First of all, the test is passing, so we know that it works. It's modular, it's loosely coupled, it's high cohesion, it's good separation of concerns, and it exhibits information hiding. So those properties that we value as hallmarks of good quality in code, 2 bits of code, however you write them, whatever technology, if one is more modular, more cohesive, more loosely coupled, better abstraction, better separation of concerns, it's better. It just is, whatever the nature of the system. So now we've got the skill and experience of a developer. We don't throw that out. We still have people that are better than other people. We still have people that are more talented and can do a better job, more experienced and can do a better job. But now we've also got this approach that anybody can apply that makes us more effectively put these properties that we value in terms of quality in code into the code. And this is much, much deeper than simply the trivial idea of having a test that says, yes, it passes. This is about the design of the code. This is about the structure of the code that we create as a result of following this practice. So this is kind of like a talent amplifier that allows us, that encourages us to make our code more modular, more loosely coupled, a better separation of concerns. And so it's not going to make a bad software developer great, but it will make a bad software developer better, and it will make a great software developer greater. It kind of turns up the volume on however good you are, in my opinion. I want to give you a demonstration of what it is that I'm talking about. So we're going to run through this quite quickly, but here's a very simple class. Here is a car, and it's got a petrol engine. And when we start the car, we're going to put the car into neutral, so that and then we're going to apply the brakes, and then we're going to start the engine. So let's write a test for that now. Here's our car. Should start car engine. We're going to create a car. We're going to say start. And then there's nothing that we can assert. So this code is not testable. So, and that's because we kind of did it the wrong way around. We wrote the car engine first, and then afterwards we wrote the test. So now, you know, the only way that we could test this would be do something horrible like brake encapsulation of the car or something like that, or really, really unpleasant. Let's start the right way around. Let's do the right thing. Let's write the test first. I'm not writing the test first, by the way. Here's the better car. So now we've changed the car. So here, this car has an engine, sure, but now we're passing the engine in from outside. So everything else is the same. That's the change that we've made. We've introduced the car, we passing in the engine, and that changes what we can do. Now let's try and write a test for the better car. So we're going to create a fake engine. What's a fake engine? Well, here's my version of a fake engine. All this engine does is that when we say start on this engine, it just says that it's been started, and then later on we can ask it whether it was started. In reality, if we were doing this in a real code base, we'd probably use a mocking library or something like that. But it's easier just to demonstrate this idea and show you that mocking is not that complicated. We're just going to give it a fake engine. That's all we're going to do. Now we're going to create our better car with the fake engine. We're going to start the car, and now we can say, did the engine start successfully? And we've got a test. Okay, so that's nice. It's testable. The testability of the car, you know, had an impact on our design. But what does that really mean? Let's imagine now we want to write some code and we're going to use the car. So now we can create a better car. The original car, we created it and we got a petrol engine. That was it. That was the only way it worked. But this code is more modular. It has a better separation of concerns between the engine and the car. It's more cohesive. The engine bit will be in the engine, and the car bit will be in the car, and so on and so on. So this is better code. So we can create a better car with a petrol engine, or we could create a better car with an electric engine. Same car, different engine. We could, if we were some kind of crazy person, we could create a better car with a jet engine. We've now got flexibility in our code that didn't exist before, and that flexibility exists because we made our code testable. So we can use the testability of our code to enhance the quality of the design of our code in a much deeper way than just saying, does the test pass? We can have an impact on the design that makes that code more flexible, open to different and more interesting usage patterns. The other idea that I was talking about that I think is a useful tool is the idea of deployability of our systems. And this is closely related to one of the things that my name is associated with, which is continuous delivery. And this is a continuous delivery deployment pipeline. And the objective of a deployment pipeline, which some people often miss, but the objective of a deployment pipeline is to go from commit to a releasable outcome. We want to build a pipeline that's going to do everything necessary to say, yeah, this change is releasable, it's safe, it's ready to go. And to do that, we need to build something that's releasable. We need to create a releasable thing, a deployable thing, and we want to test its deployment along the way. It defines the scope of our evaluation. What does deployable mean? It means that there's no more testing to be done at the end of a deployment pipeline, no sign-offs, no integration tests with other components of the system. It's all kind of done within the scope of a deployment pipeline. So we have to take these ideas seriously. If we want to achieve that, we have to worry about the modularity, the information hydrogen, separation of concerns, abstraction, to have deployable units at the right scale to allow us to make changes to manage our system simply. This has a significant impact on the large-scale architecture of our system. You could think about the difference between monoliths and microservices, both of which are perfectly sustainable in a continuous delivery environment, but they take different approaches. So it has an impact on the way in which you approach the development, testing, deployment of your systems. So these ideas are tools that allow us to scale software development. But what does scaling really mean in this sense? Well, there's kind of the naive way. We can scale the size and complexity of the systems that the way that on which I'm talking about. We can scale the size and complexity of our system. And then there's the kind of naive way, which is we can scale the size of our organizations to create change more quickly. That's a tricky, slippery slope. We'll talk about that. It's important, but it's often misunderstood. Too often what organizations try to do is what Fred Brooks pointed out in 1970 in the still fantastic book Mythical Man-Month, and he said you can't make a baby in a month with 9 women. There are limits on how far you can parallelize problems. In this case, having a baby is, there's a fixed unit of time that is at the heart of that problem that you can't really shorten in any practical way. You can average out a baby per month with 9 women, but you can't make a single baby in a month. It's not possible. This is kind of real. We've understood this for a very long time. And as I said, the Mythical Man-Month, written in 1970, if you read it today, it's, apart from the actual computer systems that it describes, all of the other ideas in it are still true of the mistakes that we make in software development. Here's one of the mistakes, is that just throwing people at a problem. There was a lovely study, which I like, of over 4,000 completed projects, looking at including real-time embedded systems, all sorts of different kinds of projects. And they divided the groups, the teams that finished those projects, into 2 groups. Teams of 5 people or fewer, and teams of 20 people or more. And then it's kind of a metadata analysis kind of research. Then they just looked into the repos and kind of figured out how long it took each team to get to 100,000 lines of code. I think if you guessed, you'd probably guess that the team of 20 people got there first on average, and you'd be right. But on average, for all of the teams, it took 9 months. For a team of 20 people, on average, they finished 1 week sooner over a 9-month period than a team of 5 people. So a team of 20 people is nearly 4 times less productive than a team of 5 people. And then when you look at the quality of the output, the team of 20 people created 5 times as many defects on average than the team of 5 people. So small teams are important. Small teams work. So if we want to scale up development, we need to work as group small teams. There's some fascinating deep stuff behind this. Classic organizations are usually organized in some kind of hierarchical structure, rather like this. And there's this weird number that keeps cropping up. If you have a structure like this, then this number of 0.85 or 85% crops up all of the time. If you double an organization that's structured like this, its capacity will increase by 85%. It won't double. It'll be 1.85 will be the factor. There's the opposite way around, though. The infrastructure costs that you need to support twice the size of the organization also only goes up by 85%. We're often familiar with that idea. We call it economies of scale. So these interesting properties. There's another way of organizing groups, information, whatever it is that you're interested in. And that's this kind of local network effect. You have these small, largely independent groups. This is kind of the social network effect in some ways, if you like, the small distributed groups. This is how some very large organizations are structured. Now, the number that's associated with this graph on the right is 1.15. This is how Amazon works. If Amazon doubles in size, it more than doubles in productivity. It more than doubles in revenue. Now, it has to pay more than twice as much in infrastructure costs to double in size, but it more than doubles in productivity and revenue. This is kind of maths. This is maths from somewhere called the Santa Fe Institute, talking about nonlinear dynamics. And there's some deep stuff going on here. So if you want to, really scale, the way that you do that is you build your organization out of small independent teams. Now, what you are doing in effect is you're trading off something. If you want your software, let's get back to software. If you want your software system to be consistent and cohesive and there to be no duplication, then you must do the thing on the left. But that's less efficient. You're going to go slower. There's a cost to achieving that consistency. If you want your software, if you want to maximize the rate at which you produce features or functions or value that software represents in your organization, you do what Amazon does. You distribute the problem so that, and relax consistency. And you can see this in Amazon's product. If you look at AWS, there were in 2020, I think that there were more than 2,000 changes to services in AWS. By different teams across the board, and there's overlap between what those services deliver, and there are big differences between your experience of how to use that, the style of the APIs, the consoles that to administer those services, and so on. They're all different and distinct, and they are not cohesive. You don't get a common experience across the board for all of those things because Amazon have consciously relaxed that constraint of consistency. But those are the costs that you need to pay in order to be able to scale. The picture on the right is the most scalable way to grow an organization, but it comes at the cost of relaxing consistency. The picture on the left is the most coordinated way of making change, but it comes at the loss of efficiency. You can't have both. It's not possible. So to scale up, problem solving needs to be distributed. That means teams need to be independent. That means they need to be working discreetly from one another. And then ideas like loose coupling and so on become even more important. If you want to work in these sorts of organizations, what does it mean to have what does leadership mean for an autonomous team? Well, the team itself is going to be making most of its decisions. It's going to be working fast, gathering feedback, learning, adapting, refining, and you want that to take place. You don't want to be giving teams like these detailed instructions. You don't want to be telling them exactly how to solve the problems that are before them, because then you are coordinating them and you're slowing them down. What you really want to be doing is leadership is now about defining kind of broad vision, strategic intent of what it is that they're meant to achieve, and defining what the boundary parameters are, saying you're responsible for this within this boundary, Go ahead and do wonderful things. We're heading in this direction over here. You want to try, try and head in that direction, but figure out how to do it yourselves. And then there might be some common stuff, common platforms, and so on, so that each team is not repeating lots of work. So you could think of some of the AWS services as an example of that. Things like S3 and queuing services and relational services and so on that AWS provides were built originally to support internal teams, autonomous teams building their own stuff. But that platform can't force change on the autonomous teams. It needs to be more independent than that to facilitate this kind of model. Some other ideas that kind of help you breed the autonomy of a team. You want the team really to take ownership. One of the things that I like to do in teams is to establish these whiteboard models. The picture on this notepad here is a real whiteboard model of a system I was involved in building. The idea is to, what you'd like is that if somebody comes and asks for a new feature in the software that the team's responsible for, you'd like them to get a reasonably consistent answer. Doesn't matter who they asked. So the team need to have some kind of consistent picture about what it is that they're building, how it works, how it hangs together. So what you really want is you want an accurate but vague working model of the system. You don't want it to be too precise. So you don't want a detailed UML diagram or something like that. You want something that's intentionally a little bit vague, because you want room to change your mind and to change the design without throwing away this picture every time. But you also want it to be accurate enough to be a tool. I kind of like to think of this as kind of a tourist map for the workings of the system, so that everybody can kind of, you can kind of figure out where you are, but you don't get lost in the detail of what's going on. Avoid too much detail. I've said here, use the tool to introduce new team members is a good way of kind of refining it, keeping up to date. And you want the reason why I call these whiteboard models is that ideally what you're looking for is that any member of the team, certainly the senior members of the team, should be able to recreate this picture from memory. And the reason that I like that idea is because it limits how complex this picture can be as a result of it's got to fit in your memory. You've got to remember it well enough. Pair programming is another tool that I think helps you scale an organization. Scaling an organization is not just about the technicalities or the dependencies between teams. It's also about the culture that you breed around engineering practice. And I know of no better way to grow and spread good culture in an organization than pair programming. Actually, I'd say pair everything. We started off by saying software development, software engineering is a creative discipline, and people are at their most creative when they're bouncing ideas around and not just sat in a cubicle somewhere with their headphones on. So I think that one of the last things in terms of scaling as an organization is to think about how you grow this in an organization. And certainly when you start thinking of the role of leaders and of any kind, but technical leaders for sure, is that the role is not to command people what to do or instruct in detail what to do. It's not software development by remote control. The guide of leaders is really to teach, to guide, to help people get the best out of themselves and then allow people to solve problems for themselves. That's really what we're trying to establish if we really want to be able to grow effective organizations. Fundamentally, what I'm talking about here is that if we want to scale up, decision-making needs to be pervasive, distributed, and carried out all of the time. And so we need to organize our work to allow for that distribution, pervasion, and continuity of decision making. That's the end of my talk. Thank you very much. I hope I've got a few minutes for a chat now to answer any questions.
Thank you so much, Dave. Always a pleasure.
No, it was a horrible session. Totally hated it.
Really insightful. And I've got two questions which probably could be the topic of yet another set of conversations and sessions. But the first one, Speaking of hierarchical structures, tree-like, if they want to change, to transform, in your experience, what do they do? How do they even have the courage to start doing that? Do they acknowledge the need for that?
It's exceedingly difficult because they are such different philosophies. It's a genuine paradigm shift for an organization to make that transition from the first model to the second. It's not always the right thing to do, I would argue. It's not always essential. I was trying to be balanced when I was describing the two, the pros and cons, which I generally like to do when I talk about things. But certainly it's possible. I have one of my regular clients I've been working with for a few years now who are on that journey. They are moving towards a much more distributed way. The difficulty is in any kind of traditional organization that's been around for any length of time is that they've kind of built up behaviors, organizational structures that kind of have embedded in them the assumption of that kind of hierarchy and control. So things like budgeting, rounds or sign-offs from managers to allow things. All of those things need to go if you're going to really buy into this, if you're going to drink the Kool-Aid. And people are loath to let things go. It's a very effective way of working. But the other big deal that people don't like coming at it from a more traditional organization is that relaxation in consistency. One of my clients, two teams made some changes and they used different graphics to indicate success in a user interface. One team added some kind of smiley faces, another one added some ticks, and people in management went crazy that these things were different. They were in different contexts. You probably wouldn't see them at the same time, but you've got to decide whether you care about that enough to go slowly, because you are going more slowly. That's the deal, it seems to me.
Mm-hmm. Yeah, so you need to have enough motivation to see the advantages, because otherwise, I mean, you are like prisoners of what got you there successfully, probably. But if you want to change, then you need to have enough drive and motivation.
Yeah, also, one of the things that I love about software development is that it's genuinely difficult. I like that it's hard. It interests me. I'm a curious person, and there are never any simple answers. There are very rarely any simple answers to any of this stuff. And I think that we tend sometimes to jump on bandwagons too quickly. So the current one, the one that I'm talking about in code here, is microservices. Everybody thinks that microservices is the right way to go. I have a very good video on my YouTube channel if people want to see what I mean talking about that. But microservices is an organizational scalability ploy. It's exactly what we were talking about in this video of freeing up teams to work independently. And that comes at a cost. There are technical costs associated with that. It's a much more complicated way to build systems architecturally to get that right, because each of the pieces needs to be independently deployable in a genuine microservices environment to get the freedom to be genuinely scalable. So there's a lot of complexity here, and it's kind of interesting. And I have been and seen small teams, we made up of 15 or 20 people that are using microservices, and you're thinking, that's a mistake. You're doing more work than you need to get the results that you're after.
So it always interested and amazed me the way that the organizational structure influences all the technology aspects.
Conway's law does exist.
Yeah, absolutely. I had an interesting engagement with a client a little while ago who they'd built a system in a very traditional manner, and then they'd read all of this agile stuff and all of this, the independent team stuff, and they just organized the teams and broken the teams up into functional groups and said, right, you're independent teams. So the teams all took a branch of the code base because they were fed up of their code getting broken all the time by other teams. And I saw them 18 months later, and their code hadn't all compiled together for 18 months. so they hadn't been able to release anything. They were kind of trying to go against Conway's law. The software had been built in one kind of mindset, and then they tried to apply another one, and that's difficult. It's more complicated than that.
Right. So, is it the trilogy ending? We hope not.
I'm sure we can talk. If you invite me back and I'm free, I'll come.
Would love to have you back at Codecamp.